like to explain application of Malus's law with a quarter wave plate. Okay, this is a quarter wave plate. This tiny transparent piece is actually the quarter wave plate, which has been mounted in a circular scale graduated from 0 to 360 degrees. You can orient the quarter wave plate in any direction. The pointer will tell you what is the angle. But of course, the quarter wave plate has some characteristic features which you cannot make out by simply looking at the quarter wave plate. So to explain that, I am modeling it with the help of some acrylic sheets. So in my model, this is my quarter wave plate. The quarter wave plate has one axis which is known as the optic axis, and the direction shown over here with a scratch is the perpendicular direction. Now what do I mean by optic axis? It is that axis when a light beam falls upon the quarter wave plate, if it makes an angle with respect to the optic axis at an angle, let us say equivalent to theta, then this electric vector divides itself into two rays. One is known as the extraordinary ray and the other one is called the ordinary ray. The extraordinary ray has its electric vector parallel to the optic axis, and the ordinary ray has its electric vector perpendicular to the optic axis. The quarter wave plate is made of a birefringent material, and as a result of this, the extraordinary ray and the ordinary rays have two different velocities. Sometimes the extraordinary ray moves faster than the ordinary ray, and therefore the optic axis is also sometimes known as the fast axis and the slow axis. Because of the difference in their velocity, when a light beam passes from this side to this side, because of the thickness of the quarter wave plate, when it emerges out of the quarter wave plate, the two rays, E ray and the O ray, have a path difference of lambda by 4. That is the reason why this device is known as a quarter wave plate. Now what happens due to this path difference? There are two electric vectors perpendicular to each other having a phase difference equivalent to pi by 2 or a path difference of lambda by 4, as a result of which the two vectors combine to give rise to an elliptical wave. What do I mean by elliptical wave? The electric vector is no more along this direction or in this direction. It starts moving along an ellipse having a major axis and a minor axis. What is the major axis? If the electric vector over here is equivalent to E, and if this angle is equivalent to theta, the component of the electric vector along the optic axis is E cos theta, and the component along the perpendicular direction is equivalent to E sin theta. E cos theta is the major axis, while E sin theta is the minor axis. Therefore, the ellipse will have a major axis E cos theta, a minor axis E sin theta, and the tip of this electric vector will keep on moving along the surface of this ellipse, and therefore this light is known as an elliptically polarized light. But there can be some special situations. When the electric vector is making an angle equivalent to 45, E cos 45 is equivalent to E sin 45. Therefore, the major and the minor axes are equal, and in that special case, the ellipse is a circle. On the other hand, suppose this electric vector was parallel to the optic axis when it entered, then it will come out parallel to the optic axis only. The component in the perpendicular direction will become equivalent to 0. Therefore, this becomes a linearly polarized light having its component E cos 0 equivalent to E itself, which is equivalent to the maximum value of the major axis, and the minor axis becomes equivalent to 0. It can also happen the electric vector when it was incident was along this direction. So when it comes out, it will again be a linear vector along this direction, having the maximum minor axis, which is equivalent to E9 sine 90, hence E, and the major axis will become equivalent to 0. Therefore, in short, if the electric vector is making an angle equivalent to 0 or 90 with respect to the optic axis, it turns out to be a plane polarized light. If the electric vector is making an angle equivalent to 45, it becomes a circularly polarized light. For all other angles between 0 and 90, it is an elliptically polarized light. That is the function of a quarter wave plate. Now, what happens to the intensity and how Malus's law can be used for the quarter wave plate? I am explaining by keeping the quarter wave plate between two polarizoids. Let me first keep the transmission axis of the polarizer vertical, while the transmission axis of the analyzer at some angle not equivalent to 90 in a general case. And I keep the quarter wave plate between these two polaroids, which is the polarizer and the analyzer. Let us say the optic axis is making an angle theta with respect to the transmission axis of the polarizer. This angle between this and this line is equivalent to alpha. And let the angle between this line and this line, the transmission axis of the analyzer, be equivalent to alpha. Okay. Now, if the electric vector E is coming out of the polarizer along the transmission axis, it will make an angle theta with respect to the optic axis when it is incident on the quarter wave plate. So the electric vector is along this direction, while the optic axis is along this direction. It is making an angle equivalent to theta. Therefore, the two vectors parallel to the optic axis and perpendicular to the optic axis will become equivalent to E cos theta and E sin theta, which I mentioned are the major axis and the minor axis of the emergent elliptical wave. Okay. Now, these two vectors, one parallel to the optic axis and one perpendicular to the optic axis, when they are incident on the second polarizer, the electric vector along the optic axis makes an angle equivalent to alpha with respect to the transmission axis. Let us say this angle is equivalent to alpha. And the electric vector in the perpendicular direction, which is like this, is making an angle equivalent to 90 minus alpha. I am interested in knowing what is the intensity after it emerges out of this analyzer whose transmission axis is along this direction. The intensity along the optic axis will become equivalent to E squared cos squared theta, and the perpendicular direction, it is equivalent to E squared sin squared theta. We'll talk about one of them at a time. So this light is incident on the analyzer at an angle equivalent to alpha, and therefore using Malus's law, the intensity of this would become equivalent to E squared cos squared theta into cos squared alpha. We are interested in using Malus's law for the quarter wave plate placed in between two polarizers, the polarizer and the analyzer. As mentioned before, if this angle is equivalent to theta, then the component of the electric vector in this direction is E cos theta. Hence, the intensity will become equivalent to E squared cos squared theta. And the component in the perpendicular direction is E sin theta, and therefore the intensity will be E squared sin squared theta. Okay, let us see what happens to the intensity when it emerges out of the analyzer. Since this optic axis is making an angle equivalent to alpha with the transmission axis of the analyzer, the intensity of light using Malus's law for this component will become equivalent to E squared cos squared theta into cos squared alpha along this direction. The component in the perpendicular direction is equivalent to E squared sin squared theta, and this is making an angle equivalent to 90 minus alpha with respect to the transmission axis. Hence the intensity when it emerges out of this analyzer using Malus's law would become equivalent to cos squared 90 minus alpha. The resultant intensity when it is emerging is equivalent to the sum of the two intensities, and therefore it is equivalent to E squared cos squared theta cos squared alpha plus E squared sin squared theta into cos squared 90 minus alpha. This is according to Malus's law. Since all the while I was talking about the polarizer and the analyzer being crossed, if I turn the transmission axis of the analyzer to make it perpendicular to the polarizer, then alpha in this case will become equivalent to 90 minus theta.